Today's webinar is on maximizing your debug productivity with ModelSim and Questa. So the agenda for today, I'll give a brief introduction. We'll talk about how to get help within the tool and outside of the tool, some general properties of the ModelSim Questa GUI. We'll spend a little time talking about the ModelSim projects, not necessarily my favorite feature, but I'll mention it anyway. We'll talk about managing your simulation messaging, source code debugging. We'll talk a lot about working with the waveform viewer, and then finally the memory viewer, and I think I'm missing one here, the advanced data flow, but we'll get to that. So to start with, ModelSim is a great tool. There's a ton of debug, but there's also, you probably, even if you've been using ModelSim for years, like me, occasionally you'll come across a feature that you're like, I didn't even know that was there, and I could have used that. So what we're going to try to do in this webinar is talk about the GUI, show you how to be more effective in using the GUI. I also do have some labs that go along with this, so if you are interested, I can either point you to tutorials within the tool, or I can send you some lab material that we have. So the first thing I like to say for Windows users is if you have a shortcut on your desktop for ModelSim, one of the things I like to tell people is, sometimes when you start up the tool, the first thing you have to do is go change the directory to your working directory. And what you can do is right-click on that shortcut, and this is more of a Windows thing than a ModelSim thing, but you can set the start in directory. And by default, that is down in this example directory in the install for the tool. But if you go and you change that start in directory, you can change that to be your project directory. And then if I'm working on several different projects, I'll put a shortcut for each one of those on my desktop, rename the shortcut to be that project name, and then set the start directory to there. So that's just a useful little tip for Windows users. So next we'll talk about getting help. If you don't already know, when you bring up the tool and you go over to the help on the top level command, there's a couple of different tabs here that are interesting. The first one is the Infohub, and the Infohub is a searchable HTML database. So if you've got some question, maybe you're using the vsim command to launch your simulation, and you want to know what the different arguments for vsim is, you can go up to Infohub, and then you can just type in the word vsim, or you can type in some argument that you're trying to figure out, and it will bring up a search of all the different documentation. And it will search through every different available piece of documentation. So that I find is a really useful thing. The other place that you can go is this PDF bookcase. And the PDF bookcase brings up PDF versions of several of these different manuals. So if you're reading about a task, I find that sometimes the PDF version is easier to look at. So some of the things you might want to look at is the DE, ModelSim DE, Questa Core, whatever you are, reference manual. So the reference manual is going to list every command that you can use at the tickle command line or put into scripts, and all of the different arguments for that command. So if you go and you say, okay, I want to pull up, in this case, the vsim command, you click on that, it's going to give you every single argument. You can then click on that argument, and it'll take you down to a full explanation of what that argument does and how it's useful. A couple of the other things that are available in that PDF bookcase, the reference manual, as I said, is the commands. The user manual kind of describes different tasks and what the steps are to do those tasks. So that's more of a procedural manual than a reference manual. There's the tutorials, which is a set of tutorials on different topics. So if you're trying to learn to use, say, the data flow window, you can pull up the data flow tutorial. It will direct you to where there's a lab that's installed with the tool and let you run through and test that. And then the thing that's actually not listed here, because this is a kind of an old slide, is there is now a GUI reference manual, which will have some of the same information that I'm going to go through today in this presentation. So just the general ModelSim commands. One of the things that you'll notice in the GUI is that there's some color coding to different things, and there's some shapes. And so the color coding actually means something. If you see light blue here, these are all Verilog blocks. Dark blue, these are all VHDL blocks. This green, that's System C code. And then the shapes, the squares, these are instantiations. So in Verilog, this is a module name. This is a module name. In VHDL, actually that's the instance of a module, but you get what I'm saying. In VHDL, the squares are entity architecture instantiations. The circles, these are going to be always blocks. In Verilog context, they're going to be processes or tasks. In VHDL context, and then over in the wave window, you get the same kind of thing. The dark blue is VHDL signals. The light blue are Verilog wires or regs. Green is going to be System C signals. And then you'll notice sometimes you'll see like a little diamond with an arrow input. That is an input port. These are output ports, input ports, output ports. Things without the arrow, those are just signals. And then also, if you're using system Verilog concepts like assertions or cover directives, there's some shape that will show up in the wave window again. So triangles are, this is a system Verilog assertion. That is a PSL assertion, property specification language. These chevrons, that's cover directives. And then when you put an assertion, that automatically includes all of the signals that are used within that assertion. So just a few pointers on the context of those colors. As we said, ModelSim, great tool. There's a lot that goes on in the GUI, and the GUI is very configurable. So there's different views that are set up automatically, and then the user can configure those views. I'll show you that. You can position any window either within the docked frame, or you can undock any window. There are these things called tab groups, which I kind of display on this picture. So a tab group is, you could pick up this window and you could move it over to the center of here, and then that tab objects would appear within this tab group. And so you can quickly switch between windows within a tab group. You can select a tab and drag it off and then position it somewhere else within the window. And that is all kind of controlled by this bit up here in the top of the tab window. So this little bumpy handle is where you can drag the whole tab group, and you can drag it to another spot within the window, or you can match it up with another tab group. The plus sign here, that will maximize this tab group to take over the whole GUI, and it'll actually make everything within one tab group, so all the windows will just be in one big tab group. This little out arrow allows you to click that and pop that window off the cockpit, which I'd say the wave window, most people like to do that. They pull the wave window off and they put it in a separate monitor. And then the little X will close that particular window. So as I said, you can rearrange all of these windows by dragging them around within that frame, and then you can save that tab group, that configuration, as a custom layout. So you can say, save what I've just done as my layout. And then if you do that, that is available, that if you click layout, you can quickly change to my layout or whatever. If for some reason you're moving windows around and things get kind of messed up and you want to put them back to the default, you can always say layout reset, and that'll reset the thing back to the normal. As I said, you can save a layout. Once you've saved a layout, you can switch to any other layout that is available. I usually do it from up here on the main thing and go layout, but there's also a toolbar that allows you to do that. And so once you've created some different layouts or the regular layouts, Questa ModelSim operates in several different modes, and each mode can have its own default layout. So the modes are no design loaded. That is when you first start the simulation or the GUI, but you haven't loaded up a design and you're not simulating. So that's if you're doing compiles within the GUI or you're doing some other things. That is what's called the no design loaded mode. And then you can click on this and you can pick what layout you want to use for that mode. Simulate is when you say vsim and you load up a simulation and you're actually running a simulation. And again, you can drop down and say, what layout do I want in that? That is probably the two modes that most people are fairly familiar with. But there's a couple of other modes. There's this one called coverage, and that's if I launch either functional coverage or code coverage. So if I'm collecting coverage data, I can go into this coverage mode. So as soon as you launch a simulation and you say -cover, because you're collecting code coverage, it'll say, okay, I'm in coverage mode, let's use the coverage layout. And then the last one is if you're doing verification management, which for ModelSim is probably not a mode you're going to use a lot. That's probably more if you're using Questa and using some of the advanced verification methods. So anyway, I can do this configure, and I can pick whatever mode it is that I want to go into when I go into these different tasks. So these are all the default ones, but maybe that my layout that I created in the last one, that's what I want to go into when I simulate, because that's got the windows and the way I like them, and it's got the wave window over on a different monitor. By default, it will save whatever the last layout you did, and it will automatically save that, and it will automatically go into whatever that mode was. If you quit the tool, it will go into whatever the last mode you left it in. This one is, these layouts, I think they're actually saved into the registry by default. If you check this box right here, it'll save it in the current project directory, in the current work directory or sim directory. And that way you can have different layouts for different projects if you want them. So the ModelSim toolbar. So depending on what you're doing, this ModelSim toolbar is kind of context sensitive. So depending on what windows you have open in your GUI, toolbars will be added and subtracted from this toolbar. The things I use most often are probably the cursor one, where I can add and subtract cursors. And if I've selected a signal, I can go to rising or falling edges, etc. This one is the run bar. So it's saying, excuse me, this is the compile, this is run, this is break a simulation. That's break a simulation, actually. This is run for some amount of time. This is run till the next, if you hit a breakpoint, to do a continue to run. So there's a few of the different things that are in that toolbar. You can configure what you want to show here. If there's way too many toolbars here and you just want to collect a different set, you go to a white space in the toolbar, you right click, and then you can pick which toolbar you want to be working with, and you can turn on and off the ones that are being showed. You can drag a toolbar off of this thing so that it's hanging out in space. I kind of find that I'll lose track of that toolbar if I drag it off, so I don't use that feature very often. Every once in a while, you will find that the toolbar thing gets all messed up and the layout will be just gobbling up resources with a ton of white space. If you ever see this, and I haven't seen it a lot lately, but if you ever see this, just right-click in the white space and say reset, and that'll set it back to a nice compact thing, and you shouldn't see that problem. Actually, if you do start to see that problem, it's something that I wouldn't mind knowing about just so that I can let engineering know. All the different windows, you can drag and drop signals between them. So for instance, I can select a signal in the objects pane and I can drag it over to the wave window and it'll add to the wave window. Here I had selected it and I drug it over to the transcript window. And what that did is it just said describe this signal name. And I mean, that's not really useful in the transcript window per se, but if I'm creating a tickle script that I want to do for like maybe saving wave window or something, if I'm creating a tickle script, by dragging this over, now I have the full path name to this restore signal, and I can select that path name and I can copy it into a tickle script that I'm creating. The other thing here, I'm showing the wave window, and I've selected, a block of code. And if I right click, I can say add that to the wave. And what that will end up doing is it will add one copy of every signal in the code that I have highlighted right there. And that can be useful because, if I have some code that I'm debugging, I could go find that in the objects window, but it's just maybe easier to do it that way. But I can highlight a big block of code and I'm not going to get multiple copies of any of those signals in that highlighted code. Within many of the windows, and especially the wave window, there is this concept of strokes that you can use. So that's the wave window and the data flow window are probably the two main windows that you use these. But for instance, if I have the wave window and I want to zoom out full, I click, and I think it's center mouse button. I always have to remember, yeah, it's the middle mouse button on a 3-button mouse. And if I click and I drag up and to the left and release, that'll zoom out full. If I click at the top and drag this way or this way, that will zoom into the area that I've just drug across. So let's say I'm interested in, what was going on right here. I could click and go to here and release, and it'll zoom into that area. And then dragging up and to the right just zooms out to double the size that the window is currently at. You can also do that zooming in, out, and full with the I key. That'll do, twice the size. The O key will zoom out one, and the F key will do a zoom full. So then again, the ModelSim Project tab. I actually find that the more experienced the user is, the less likely they are to use the project mode, and the more likely they are going to be to just create a tickle script that does the same thing that the project mode does. I just find that the tickle scripts, you have more control. But if you want to use the project mode, you come up and you say, I want to create a new project. You give it a project mode. You say where that project is going to be located. So that's going to be the directory for your project. You give it default working library, and then by default, it's going to copy all the settings from the installation. So once you've created a project, you then, in that directory, have this thing called projectname.mpf, ModelSim project file. And that MPF file you can then click on and it will open up the project. It is a text file, so you can edit it, you can look at it. I wouldn't make a lot of changes in this project file unless you really, really know what you're doing. So I would say be careful with making changes to that text file. So once you have a project, you can then say, okay, I want to add a bunch of files to my project. So you can say add to project, and you go through and you can, you get a little browser and you can add different files from different places, and those all then get added to as files within your project. Once those files are in the project, you can sort them to say, what's the top level, what's the next level down, etc. That will create a compile order for the files. And then once you have that project, this is the project tab, you can select a file and say compile just this file, or you can click here, that's compile all the files within the project. And then what will happen is you'll see this status, and that's going to say these files all compiled correctly. This file had some kind of an error when I was compiling it. So then you can select that guy and you can say, let's look at the compile for that. That will bring up the transcript and allow you to start debugging as to why that compile failed. You click on that message, you go to there and realize maybe there's some syntax error or something on this line. Yeah, right here. Instead of wait, I said what. For VHDL, this is the one benefit of the project mode. But VHDL, you have to know compile order, and you have to compile things bottom up in VHDL. So you can either manually set that, and so here I click compile order, and I can manually order this, or I can click this auto-generate compile order. And what that'll do is it'll go through all those files and it'll figure out what the dependency is and order the files in the way they need to be and resolve all the conflicts, so then I can hit compile and go. So once I've done that, I can hit this start simulation button. I pick my top level of my test bench, whatever that might be, and I click and I say, start simulation. And that will launch the simulation. This shows you the work library, and you pick your top level test bench. You say, oh, good, okay, and that will start the simulation. Another thing you can do is you can go to that project and you can add what's called a simulation configuration. And this will look very similar to start my simulation, but what it does is it allows you to pick that top level test bench. You can give that thing a name. Then you can go through some different tabs and set some different arguments, etc. And then you save that configuration, and that will then save this smoke test configuration into your working library, so that if you want to run that test again, you just double click on that, and it launches the simulation and does whatever you want. So opening an existing project in Windows, you can either double click on that project in like a Windows browser, or if you're already in the ModelSim browser, you can click and say open, and then browse and find that MPF file, and that will open that project. Again, I find that folks once they get familiar with how to compile, what the commands are, instead of an MPF project, they're probably going to create a compile script and a simulate script. And just the reason being is that you have a little more control once you've done that. So now let's say I'm in my simulation and I'm running my simulation and I'm getting messages that are coming out in the transcript window. So ModelSim will present those messages in a couple of different ways. So the default way is just in the transcript window, you get, as the messages come along, they're thrown out into the transcript window, and, it's just a linear collection of all the messages that come along. So that's the default way, and it's good for just looking at the simulation as it's going along. But if you're getting a ton of different messages, let's say, you're kicking out a whole bunch of different error messages, and you're trying to find data within there, if you are using the standard messaging methodologies within VHDL or within Verilog, you can arrange those into what's called the message viewer. So in VHDL, if you're using either the assert statement in your code or the report statement in your code, that allows you to, that is the standard messaging for that. In Verilog, there is the error warning note things that you can use that configure these things. And by using it that way, you are now able to collect messages of similar type and show them in this error messaging tab. So let's say you're getting a bazillion notes that are coming out and you're looking for a certain thing, you can just collapse that notes pad and just focus on the things like the errors. And then the other good thing is that once you're in this messaging tab, if you're looking at it in the message tab, you can right click on any particular message in that tab and you can say things like view the source. And that'll bring up the source code that produced that message. You can say, go to the wave for that particular message, and it'll center the cursor on the wave window at the time that that message came out. You can say that message, then you'll see if you're looking at the wave window and you've got that message tab enabled, you see these little markers that come up in the message bar at the top of the wave window. And if I put my cursor on that little message bar, it will actually pop up that message. Or I can double click on there and it'll go over to the message viewer and it'll show me what message was put out at that particular time. So it's kind of a way to go back and forth between the messages and the wave window, and it can be kind of useful. So source level debugging. So now let's say I'm running a simulation and I'm trying to track down the source of some bug, and so I'm down at debugging to the source code level. So the ModelSim source code window has a lot of different purposes. One, well, first of all, you'll notice that it's all, syntax highlighted. So all the Verilog keywords, all the VHDL keywords, they're going to be highlighted in red. All of your signals will have a different highlight color. So it's kind of good there. Now, if I look at the source code numbering, you can turn this on and off, but if you have it turned on, you'll see all the executable lines of code are highlighted red, and all the lines of code that are not executable, that are just like keywords and syntax things, those are black. So any of these highlighted ones, I can put a breakpoint next to. So anything that's highlighted red, I can put a breakpoint. How do I put a breakpoint? I just click in the column next to that highlighted keyword. If I go over here to all my signals and I just put my cursor on a particular signal and I wait for a 2 count or so, it will pop up that signal name and it will put, actually I guess it was the count value that I put it on here. So if I put my cursor on count, it pops up the full path name of that signal and what its current value is. And that value is tied to, you know, probably now, if you haven't done anything, the active cursor, if you've dropped and activated a cursor on your wave window, or you can set any particular time. By default, the source code window is read-only. You can right-click and say, and turn off the read-only and use this as an editor. I would say most people do that just to make a quick change. It's like, oh, there's a syntax error. Let me just change that and recompile and run again. I would say no one really uses this as their main editor. Almost everybody has their own favorite editor that they use for major source code editing. So then, as I said, setting a breakpoint, you basically can click in this white space right to the right of any highlighted line number. And if I click there, I'll set a breakpoint. Or I can right-click on that, and I can do a number of things. I can say set a breakpoint there. If there's already a breakpoint at that point, I can either add or remove it. I can disable the breakpoint. So there's a lot of different control I have there. So yeah, here I've right-clicked on a breakpoint. I can disable it, which means it's still there, but it's just not currently active. I can also say, let's edit all the breakpoints I currently have set in this simulation. And if I do that, it'll bring up this menu right here. So this is showing that I have a breakpoint in this code on line 102, on this file, on line 94, et cetera, et cetera. I can add a breakpoint at this point, and this is the place where I can add not line-based breakpoints, but I can add value-based breakpoints. So I can say something like, let's put a breakpoint when the address is 35 and the data is 55B or something. So I can put value-based breakpoints, and then I can select a breakpoint and I can say modify that breakpoint. So if I bring up that modify, that allows me to do a few things. Name the breakpoint, that's kind of no big deal, you know, who cares? Instance name. So if I have this particular code right here, and I have 10 different instances of that code, I can say which instance that breakpoint's going to be in. So by default, it's all instances. So anytime I hit that line in any of the instances I have, I'm going to break. So if I put an instance name, it'll only break in that specific instance. And the other thing that's kind of interesting is a breakpoint condition. Sometimes I find that you've put a breakpoint on some code and you save that breakpoint's going to be in my code. And then I start my simulation and I say go. And while reset is active, it hits that breakpoint 4 or 5 times. And I have to say run, 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 run. And then finally the 5th time, it'll start running and it'll take 5 minutes before it hits that breakpoint where I'm actually interested. So breakpoint condition allows me to do something like say, only break when reset n is a 1. So only break when I'm not currently resetting. And then the last thing down here that you can do is when you hit a breakpoint, you can actually run a do script or a tickle script. So you can say, when I hit this breakpoint, force this signal to be some value and run 5 more nanoseconds or microseconds or something. I don't use that very often, but it's kind of interesting. It's something you can do. So once I've hit a breakpoint, now I probably might want to single step through my code to figure out where it's going. So this step bar gives you several different ways to step. There's step into is this one, and that's step along through my code, but if it branches off to some other function call or task call or whatever, go ahead and follow that task call, step through there, and then step back when I'm done. So that's step into. Step over will be, I'm in this code, I'm stepping along, and if I get a task call, go ahead and run that task, but don't step into it. Run all that task call code and go to the next line within this file that I'm currently in. And then step out of is similar. It's in here, and if it steps out of the code, follow it. And there are two different types of step functions. There is a complete step, and there's a thread-aware step. And if you use these, that will stay within the current simulation thread. This really becomes, for standard VHDL and Verilog code, these two step functions will probably act very similarly. It's really when you get into system Verilog code that the thread-aware stuff starts to matter. So source code annotation, if I'm in the source code window, I can either right-click and there's a menu there, or I can go up to, the source, and I can click this Show Source Annotation. And if I do that, what it does is it shows every user signal that's been defined. It shows the value of that signal right underneath it. And so you'll see right here on the clock, I obviously have my cursor sitting at the rising edge of clock. I have my cursor sitting on that, so I'm seeing that the value of clock is that it is currently transitioning from 0 to 1. I kind of feel like usually this is overload when I'm trying to debug, because remember, if I just put my cursor on a value, it'll pop up that value at that moment. So, and then again, this time is most likely going to be tied to the active cursor wherever you drop it, but you can right-click on there and set an absolute time to go to. Editing source code. Again, you can go out of read-only mode and do some simple edits, but I really don't find that anybody is going to use this as their main editor. So that's kind of source code annotation. Let's move on to viewing and working with waveforms. So the first thing I want to talk about is the waveform log file, the WLF file. By default, when you run a simulation and you're recording any waves, it's going to get stored in this file called vsim.wlf. That's the wave log file. Whenever I add a signal to the wave window, it will start to be logged in the WLF file. So let's say I'm running my simulation, I've got a bunch of waves in my wave window, and I'm debugging, and I go, you know what, I need to look at this signal. And you go and you drag that into the wave window or whatever, and you drag it in, and there's no data for that signal. And the reason there's no data is that signal hasn't been logged. It's not currently being logged. So you need to either add things to the wave or add things to the log in order for them to get logged. So right here at the beginning of my simulation, I could do this. I could say add to log all the items in this design. And that's going to log every signal in your test bench and all the way down the hierarchy through your design. So for a small design, that may be okay, but for a really big design, you might end up generating a huge WLF file, and your simulation may slow down to super slow. So be careful with doing that. But what you can do is you can be a little more selective. You could say, you know, what I'm really debugging right now is this control instance. So you could select that control instance, click on that up here, and then say add to log all the items in this region and below. And so what that'll do is it's going to log everything in this instance and all of its children. If I just said items in this region, it'll just be the items from control instance. So that's what I find is probably your best bet, is that you want to say things like, this is what I'm currently debugging. Let's log all the items in it and its children, and that way all of those signals are being added to the log. So if at any time I add any of those signals to the wave, they will have data and I'll be able to continue my debug. So I kind of have said this before, you can get items into the wave or the log from pretty much any window in the GUI. So, you know, if I was over here in the Sim tab, I could just select this process. I could right click and say add all of those to the wave window. The objects pane is going to be all of your VHDL signals, all of your Verilog wires and regs. That's the objects pane. The locals is going to be things like VHDL variables, signals and regs from a task in VHDL or in Verilog, things that come into and go out of existence as the simulation. Those are locals. Now, locals, you can only add them to the wave window when they actually exist. So you have to maybe run till you're in a task, have a breakpoint, and then you can add the signals, or excuse me, the locals from that task to the wave window. And then finally, like I said before, you highlight a block of code, you can add that to the wave window. So if I've got a bunch of stuff in my wave window, there's things called dividers. And adding a divider is, all it's doing is adding a label. It's just going to put a label in here that says memory and everything below that. And that's really, we don't use that as much anymore because now for, you know, about 10 years, we've had this concept of groups in the wave window. So with a group, what I do is I select all of these signals, and then I say right-click, group them. I'll say that's memory. That's going to be a group name. And now what that does is it creates this group. So it's like a divider, but at the same time, I can also hit this plus or minus to either collapse or expand that group name. And that's a way that you can put a lot more in the wave window and have some control over what you're looking at. So by default, all the signals within the simulation are going to be in this symbolic radix, which basically means multi-bit signals are going to be shown as binary. I'm not really sure what the difference between symbolic and binary is, but I will say what I normally do is I set my default radix to hexadecimal. You can do that as a runtime option here, or you can go and edit your ModelSim INI file, search for the word radix, and set it to hex. Then what will happen is that all of the signals will show up in that default radix. Right now, that was set to binary, and if I go and I change that to unsigned, it'll now show that as an unsigned variable. And that's going to be every window in the design. So that'll show it in the objects window still as hexadecimal. It'll show it in all of the different windows. Once I've set that, I can override the default radix or just one version of that. I'm not going to go deep into that. So let's talk about wave cursors. So cursors in the wave window, once I put a cursor, you'll see I have two cursors, and I can drag and drop. I can select this cursor down here. If I click on this label, and then let's say I go up, I left click, and then I go up to this signal right here, maybe address, or in this case, clock. And as I get close to an edge, that cursor will snap to that edge. So it'll be right on that. And then I could go down and select this cursor and move it over to like here, and it'll snap to this edge. And then once I do that, it shows the time between any two cursors. So I can add a cursor or subtract a cursor with these. If I select a signal name, and then I can say go forward to the next edge, go backwards to the next edge. I can say go back to the last falling edge, go forward to the last falling, back to the rising, back to the falling. So I can move around on edges by selecting a clock and then clicking these, and it'll bring the cursor to whatever edge is next. Time between cursors is shown. Active cursor is highlighted. I can click on these lock buttons to lock down a cursor, or I can click on this button, which brings up a menu for setting some properties, and I'll show you a little more of that on the next slide. So properties on a cursor, I can right-click on that cursor and I can change its name. Again, I kind of, don't really care about changing that name. Locking a cursor will mean that that cursor is now locked fixed and I can't move it. If I click on that little menu icon right here, I can bring up this Windows Preferences thing. And so then a couple of the things I can do in the Windows Preferences is I could check this box that says show frequency instead of time, and that'll show that as a frequency value. I'll show you some more things on that in a second. So again, let's say I'm looking at this and I got, this event, and what I really want to know is how many clocks did it take from 0 to get to there, or something like that. And so again, I can bring up that menu here, and I'm doing this grid configuration. And so I know that my clock is 122 nanoseconds. And I know the first rising edge happens at 61 nanoseconds. So I'm going to set, those two grid configurations, and I'm going to say display grid count instead of time down here. And so I do that, and what I'll see now is instead of showing time down here on the x-axis, I'm showing number of clocks. So I can see that this event happened at the 325th clock. And if I put two cursors, it'll show me clock count between those cursors rather than time. Another thing that I can do with that menu is I've switched from the thing to the display, and there's this little thing that says number of elements. So if I set the number of elements to 0, it's going to show the full path. If I set it to 1, it's just going to show the signal name. If I set it to 2, it's going to go show the signal name and the instance that instantiates it. So those are probably the three values that I'll use. 0 to show full path, 1 to just show signal name, and 2 to show the signal name and the cursor or the thing above it. You can toggle between full path and just the name with this little button right here. The other thing that I always set up is what happens when I double click on a signal in the wave window. And I almost always go to this and I say show that signal in the data flow. And I'll talk more about the data flow in a little bit. So once I have gone through and I've added a whole bunch of signals and names and everything else to my wave window, let's say I've created some wave groups and some other stuff, I'm logging a certain set of signals. I've gone through and I've set up this wave window for a particular simulation. I always want to go and save that format. And so if I click Save Format, it will then, in my working directory, it'll save by default a file called wave.do. I can name that anything I want, but the default name is wave.do. And that's going to save all of the wave format information into that wave.do file. And then I can call that wave.do file up the next time I run a simulation so that I have all the same waves and stuff in there. I can also edit that wave.do file, and I can make changes. The format is pretty self-explanatory, and I can add signals, I can add wildcards, I can add all kinds of stuff to that wave.do. So let's switch gears for just a second, and let's talk about concurrency in sequential software. So a simulator, a VHDL or a Verilog simulator like ModelSim, we are simulating a bunch of gates that are all acting in parallel. But the simulator itself is running on a computer, which by nature is a sequential event simulator. And so the simulator does one thing at a time, but there's a, kind of a simulation queue that helps you to simulate all these parallel events that are happening. And so sometimes you will have issues with things like race conditions. And there are 0 time delay steps that happen. So here is a example of VHDL code that is going to cause event ordering issues that happen in 0 time. So what it looks like I have here is a shift register. And so I have a clock, I have a couple of registers, I've got data that's coming in. On one clock cycle, I expect data to go to D1, and on the next clock cycle, I expect it to go to the output and then flow to the output of this port. But you'll see what happened here is my designer was kind of sloppy. And what he did was he assigned clock to clock 1 and clock 1 to clock 2, and I've collected code that's spread out all over the place into one module here to demonstrate an issue. So you'll see reg 1 is being clocked by this guy, and reg 2 is actually being clocked, and I've got the wrong name here, I just noticed, by CLK2. And if I simulate this code, what I actually end up seeing is it appears I have an issue. It appears that this code on one clock cycle, let's say everything is 0, and then I put a 1 here and clock comes along. When I simulate, I will see that the 1 goes to D1 and D out on the same clock cycle. And it's like, what's going on here? So I'm looking at this, and here is the data in as a 1. Here's the D1, the D2, and the D out. And here is that clock 1 and clock 2. And it looks like that on this clock right here, this D in goes to D1, it goes to D2, and it goes to D out. And it looks like there's a bug. And, what's happening is that there are 0 time delay effects that I'm trying to find. So it's race condition kind of things. And it used to be that you have to use this thing called the list window. And the list window would show the events, and it would show the delta times and all this stuff. And it was really hard to interpret what was going on in this list. So a few years ago, we basically added that delta debugging to the wave window. And so now what happens is I'm going to show right here, and I'm going to expand into the delta time. I'm going to expand around the active cursor. And so now what I see is here's the clock, and then that assignment. VHDL says when you do an assignment, when I assign clock to clock 1, that caused a 1 delta cycle delay. And when I assign clock 1 to clock 2, that caused a 1 delta cycle delay. So this is that clock tick 550. Here's 1 delta cycle later, another, and we'll see. Here's data in. Here's clock that's clocking that first register. So 1 delta cycle later, D1 goes to a 1. And then right here is the clock 2, and sure enough, D1 is a 1 at that moment, so that gets assigned to D2, and then that gets assigned to D out, and so it actually shows that that shift register is indeed acting like a shift register, but its clocks are skewed in delta time. And I was able to find that by diving down and expanding the delta cycles around that. Now, delta cycles are a VHDL construct, and you can see that even though I've expanded into this delta time, I still have 2 events that are occurring at the same time. So I push even deeper, and I can go into what's called simulation step time. And so that is expand into simulator event time. And now you'll see these 2 events that were happening at the same moment, I pushed even further down into simulation event time. So you may not need to go to that even further depth, but if you do, that's available. And all of that is for finding delta type events. So another thing in the wave window is something called the wave signal pattern search. So if I'm in the wave window, I can get to that by saying signal search. I say signal search, and it brings up this wave search window. So if I have selected a particular signal, I can search for the next transition, the next rising or falling edge. If it's a bus, I can search for a particular value on the selected signal, or I can do this search for an expression. So search for an expression, right now what I'm doing is I'm searching for when this signal weight is a 1, and the CPU read is at a 0. You know, maybe I want to search for when the address is 35, the data is 46, and the state machine is in transmit mode. You know, I can put whatever expression I want there, and you can either manually write out these expressions if you know all the signals, or you can click on this expression builder, which brings up all the different signals and allows you to create the Boolean expression that you want to search for. I can search for the first time that that happens. I can search for the 50th time that that happens, whatever. I can search within a certain time window. So all of these different things, I create that, I say go, and then what it does is it searches the wave database, and it's found a time when this is true, puts the cursor right there, and allows me to kind of look at the signals around there. It is possible to put signals in analog format. So analog format is I can just click on that signal. I can say change the radix, and I can set that radix to be analog. I can be an analog step function. I can have a smooth analog function. You can set the height so that you can control how big that signal is, so you can see the different things that are within there. Anyway, that's a wave window. So now let's quickly talk about the memory viewer. So what the memory viewer is it analyzes your code and it looks for any two-dimensional arrays. And there's some limit, like below a certain size, it doesn't show it as a memory. And I forget exactly what that limit is. But what this is going to show is if you bring up this memory list. So if you go in the GUI and you say view memory lists, it's going to look through all the hierarchy of your design and find all of your two-dimensional arrays. So in this case, it found 3 of them. These 2 are 128 words by 8 bits wide. This one's 16 by 8. So anyway, I find that, and then I say, okay, I want to look at this memory. So I right-click on that, and I say show the memory view of that. And it brings up this memory of this vector. And what I get is the address is shown down here along the left, and then the data is shown here. So this is address 0 through 12, I guess, or through 11, and then this is 12 through 23, etc. So by default, this is showing right now as a hexadecimal address down this way, binary data, and it's showing 12 words per line. I can right-click on there, and I can configure that. So if I right-click and I say Properties, I've decided I want to show the address as a decimal value, and I want to show the data as hexadecimal, and I want to show 4 lines per word. So I say OK, and now it shows address as decimal, data as hex, and I'm showing 4 lines per word. So, maybe that's the way I wanted to look at this memory. Once I have one of those memories, it's showing that whole value, and I can split that, and I can show 2 different address ranges. So, I can have 2 different independent scrolls, so I can see 2 different address ranges. Any one of these values, I can click on it, and I can just update that value by clicking on that value and changing the value that's in there. That's poking any one location. If I right-click on here and say change, now I can do things like over the whole address range, I want to put in random data. If I say OK, I would then get randomized data everywhere. Maybe I want to say, I want to put an incrementing value starting with 0 in every range. I could say, I want to put the value 5.5 in every location, and I'm going to skip every other one. So what that would do is it would put 5.5 here, and all the even numbered addresses would have 5.5. Then I could go back and I could say, let's start at address number 1, and let's put AA, skipping every one, and that would put AA in all the odd locations. So I effectively just put a checkerboard pattern in my memory. Once I have a set of memory or values in a memory, I can export that pattern to a file. So when I say export, I can give a file name. There's a couple of different formats. There's a Mentor MTI format. There's a Verilog hex and a Verilog binary format. I can decide whether or not the address is going to be put into that file or not. And then I can save that memory file. And then obviously, if I can save a memory format, I can also read a memory format. So importing would be, I'd say, let's import a pattern. And again, I say, what am I loading? What format is that file? Maybe, that's probably the thing that I do is I just say, it's going to be specified in the file, look at the file, figure it out. Import that pattern, say OK, and that'll read that data back into the file or into the memory. So once I can read and write memory patterns, maybe my test bench, what it does is it runs through a set of data, and then I expect a certain set of data be in some range. And so now I can do things like compare. So I can say, run to a certain time, grab this memory right here, and compare it to a saved file that I have. And so that's going to do a compare. And what it does is it uses tk-diff, and it shows the 2 memories. And right now, it's showing these 2 memories were identical. So I ran my test, and the same data was in both files. Now, let's say it wasn't the same. What tk-diff is going to show is it's going to highlight all the places where there's differences between my, golden results and the memory that is in that spot. So then the last topic we'll talk about is the data flow. What the data flow is useful for is you can add signals to the data flow from pretty much anywhere, but the thing that I normally find is that I'm probably going to be adding something when I look at, I expect it, at this falling edge of this signal that the address was going to have some value. So I'll put my cursor right there, and then I'll double click on that signal, and I'll see that it traces back that address, and it traces it back to this box right here. And what this box is in this case, it's an initial function from some Verilog code. Maybe it's a process from some VHDL code. Maybe it's an assignment statement from somewhere. So it traces back to that, and it shows that signal. Now I'll say, you know what, maybe this address is the incorrect value because this input was wrong. So I can click on that, and it'll trace back where that came from. Or I can click on the clock, and it'll trace back to where that clock came from. The data flow, you can show it in a hierarchical manner where it'll show the hierarchy of things and put a box around the hierarchy. I don't use that function that often. You also can add a wave window that is tied to wherever you have currently selected. So right now, I have selected this assign statement, and it's showing the input and the output of that assign statement right here. If I click on this initial block, it would show all of these signals in this wave window. And so it's just basically an attached wave window that is going to show whatever you click on in the data flow window. And then there's a special function of the data flow for tracing down exits. So right here I see this read write, and I see that it's going unknown. So I'm going to double click right there, and that's going to bring up the data flow. This signal right here is an X. Now if I look at that, I see that this is a buffer, and that the output is an X because this input is an X. So I could double click on that, and it would trace back to the next place that came from. And then I'll see there's another X, and I could keep manually tracing back. Or I could use this thing called the chaseX function. And so here I have selected this guy, and I'm saying chase down this X. And what chaseX does is it just keeps tracing back, and every place it finds an X, it will expand backwards from there. And so it keeps expanding backwards until it gets to right here where this is an X, but the inputs to this gate were not an X. So this was a high Z, that's bad. I've got a floating and a 0, and that's why that's an X. So where did that come from? I double click on that. It opens up the source code for that NOR gate. I can then look at all of those signals, and I can figure out which one of those signals has a problem. And if I eventually look at it, I'll find that the test in signal, I defined it, but I never assigned a value to it. So it's floating, so that's where that X came from. So that's pretty much what we were going to talk about today. So the summary is there's a whole bunch of good debug tools within the ModelSim Questa GUI. People don't always know what's there. I've given you an overview of how to be more effective. It's really just a taster. Contact me if you have questions on how the GUI works. I'm just going to say thank you to everybody for hanging in there for an hour of me talking. Hopefully this was interesting and informative. If you want a PDF version of this webinar, you can contact either myself or Molly, and we can get you a PDF version, because there was a lot of stuff we covered that may be better from a PDF than looking at the webinar. So with that, it doesn't look like we have any more questions. So I just wanted to, again, say thank you to everybody, and we'll see you on the next webinar.